This.
Absolutely.
Yeah, I felt that.
I'm even going to give an intro where we mention that this is kind of, and then we'll, absolutely, we have a tempo worked out. It's going to be good. Yeah.
Yeah, and I mean, I think there's a certain numbness that comes over for that moment.
Yeah, no, for sure. I used to do triathlon, but I didn't take care of myself. And I started doing this, and now I'm slowly getting back to taking care of myself. Maybe in like 4 years, I can get to that.
Yeah, I mean, you set your goalposts along the way, right? You
For
don't
sure.
just jump right in. And I know some people years ago, they were doing with TV training. TV training, you know,
Should I face the back
they're not so big anymore, but 10 years ago or so, they were everything. You want to do endurance events, you have to run 1 to 5. It's a charity event to raise money for the Human Lymphoma Society, but
Cool.
they take you from day one.
All right, we good? I think we're good to go. You ready? We're starting on
Yeah,
us.
I am ready.
Yeah, we're starting this way today.
All right.
Well, happy Sunday, everyone. Welcome to Hack Sunday. Thanks for joining us. I know it's a beautiful day outside, and I'm glad that other people share my enthusiasm for being inside and learning. So here we are today. Welcome to Hack Sunday. For those of you who don't know, we are a live production studio. We actually do focus here on live production. We do live streams here all the time. My music's still on. Let me turn that off. And today we're here for Hack Sunday. We're here to learn how AI is taking over the world. And today's talk started, so for anyone who missed last week's talk or didn't watch it on YouTube, we started a conversation about vector databases, which began with Gaurav teaching people in the Telegram chat, me being lost and saying, what the hell are you guys talking about? Can you please explain this to me? So we did part 1 last week where Gaurav tried to explain vector databases to me. He did an amazing job. I'm still confused as hell. But we did learn a lot, and that's the goal here at Machine Learning Together. So today we got 2 people to try and teach me. We got Gaurav and Stanley. We think between the 2 of them, maybe they can educate me here. So with that, I'll turn it over to you guys. If you want to give a quick little intro and tell us what we're talking about.
And I'm actually so excited we get a second day talking about vector databases.
Me too.
And I have to say, though, it's mostly my fault. I was asking too many questions last time. So we're just going to cut through the middlemen, and I'm going to be up here, sort of contributing a little bit to Gaurav's flow. But yeah, I think we're actually going to start fresh, kind of go through the slides, cover the main topics. And even for y'all non-technical people, the systems we're talking about underlie all of this large language model stuff. And so these tools and these technologies are going to be a big part of the rest of our lives. So,
Sure. Since we are doing like a recap, I'll do it quickly. So first of all, we'll start with what is database. So database is a technology that stores and retrieves information or data. And then we went through types of databases. We have different types of database, such as document database. Most of you are familiar with relational database. During the last talk, we also talked about like analytical database, which was like used for business intelligence, and we had a long talk about it. Then there is Stanley's favorite graph databases, and then you have like all sort of NoSQL or not a SQL database, which is like DynamoDB or and most of these databases are either column-based, or they are key-value pair, or they are document stores. So we went with them through them a little bit, and then we went with different use cases of databases that that people use. And here is the slide that explains it quite well with the examples. And we went through that one. And finally, we introduced what is a vector database. So vector database is a representation of the data in n space sort of representation, right? So as you can see in this picture, like all those points which are animals, they are clustered together, and then fruits which are data points are clustered together. So basically, what vector database stores is the mathematical representation of that data. And we did introduce that a little bit. Do you want to add something to that, Stanley?
yeah, it just, the idea here is that the relationships words have linguistically within a piece of text become geometric relationships in the space. It's a very beautiful kind of transformation. And then one thing I would love to say is that I feel like, and it's starting to become clear that our brain actually uses this to store information.
Right.
And so I always think like when you say you're reaching for a word, that's actually true in the vector database in your brain.
All right, so then we went through how do actually vector databases work. So as you can see in this slide, that there are images, documents, and audio. These are like different formats of data. We transform them into embedding. Embedding is nothing but a vector mathematical representation of that data, which we depict over here with the vector representation. And then we use some sort of nearest neighbor finding algorithms, and then those algorithms help us do any kind of query on those. Yeah, and last time we also went through some distance metrics in detail, like what's the mathematics behind it.
Gaurav, I'm so sorry. So quick too, but I just wonder,
Sure.
is there any chance you'd say a little something about what a nearest neighbor algorithm is?
Sure. So nearest neighbor algorithm, as you know, that the whole vector space, you can think it it's sort of like n-dimensional space, and now you want to find, say, suppose, let's go to the example over here. Like, I have, say, suppose I have a query which falls into like animal. Let's say, I can't think of animal. Say elephant, right? So where do elephant closely matches with this category? And that's what the nearest algorithm, neighbor algorithm would do. It will try to find the centroid of that particular cluster, and it will try to put that particular query or the sample into that cluster. Do you want to?
It's so well described.
Yeah.
And then just to emphasize a little bit, so for example, wolf might be close to dog because they're both animals. It might also be close to dog because they're both mammals.
Right.
Could also be because they're four-legged. So we think that there's all of these different dimensions of similarity.
Right.
And then the K in K nearest neighbors means it's looking at a number of different dimensions, right?
Right.
Anyway, it's just so cool. I love this picture, man. This is perfect.
Yeah, this I also love this picture because every human being has this inherent ability to think in 3D, right? We understand 3D space. We don't understand like 4-dimensionals or n-dimensional spaces. So I really love this this sort of representation of vector database, and that's why I chose this particular slide.
I have one friend who can think in 4 or 5 dimensions, and I hate her. It's such a superpower.
That's awesome.
You have a question? I'm supposed to limit the questions, but let's see.
Oh, sorry.
No, I'm just kidding.
I apologize. If you're going to get to this later, I can hold off on it. I just wondered if you could speak to the challenges of choosing vectors.
Oh, 100 million %. And then actually the main reason I'm here is we're actually going to look at a small case study at the end that relates to generating embeddings constructively. And then just for example, has anyone had the pleasure of giving an image to ChatGPT and then ChatGPT can answer questions about the image? That is what's called a multimodal learning system.
Right.
And the way that works is you take the text and you create a set of vector embeddings in the same space as you embed the images. So it's kind of like you're creating a common language for text and images. And that's a big reason why everyone's so excited about these technologies right now. But anyway, forgive my digression.
No, that's super cool. And then we dealt with a little bit on what's like the traditional search and semantic search, and I also presented like 2 real case demos that we went through. One was a very simple vector store search where it was using like it was using the semantic search. So what this demo was, I took like a PDF and I gave that PDF to a vector store, and then created embeddings from it, and then we tried to do a semantic query on it. The second demo was for images. Same thing we did for a large data store of images, but here we tried to use traditional SQL queries with a single store database. I will go through these demos again if needed, but without further ado, I would like to jump into how can we optimize these algorithms, right? Because right now it feels like you have data stored somewhere, you have these mathematical representation of data which you are storing in vector databases, and overall, like how can you optimize, how can you improve the search quality and the search efficiency? So researchers have come up with different sort of algorithms. We'll go through some of them today. So first one I would like to think about is like clustering. Since I was talking about clusters, creating clusters of data points and stuff like that. So the first algorithm that I would like to go through is clustering-based indexing, which is FIS as an example. So FIS is Facebook AI Similarity Search. It's it's like most popular in the vector databases. And what FIES does, it optimizes the query by using different methods. Most popular they use is called product quantization. And what product quantization is basically each data set is converted into more memory efficient representation, which is called PQ code. And as you can see in the image, like you have these original vectors, which are nothing but the embeddings, but then you slice them, you try to cluster those vectors, and then you finally get like the common point, which is, as Stanley said, like this common point would be, for example, four-legged mammals, right? So four-legged mammals have like one common centroid point, and they have all the animals that are like really close to each other. Would you like to
Oh no,
add
so
something to that?
so well described, and forgive me for being Mr. Asterix on this talk. I mean, just Gaurav is saying all the main stuff, so all I can do is put a cherry on top. But one thing I would like to say is, like, man, think what you will of Facebook as a social media platform, but has their engineering team ever contributed a lot to this space?
Yeah, they have, because they see these sort of problems that other world or other businesses do not see. They have like millions of people getting onto their website, and you need to have those optimized searches. You need to find your friends like within seconds, right? So they came up with these ideas, with these techniques, so that you could find the people closest to you, and you can build that social network. And again, they wanted to also try to do targeted advertising, which was like their source of revenue. So they wanted that really fast, right? You need to see an advertise which belongs to you, and like I cannot show an advertise of bike racing to a mother, right? Like she won't be interested in looking at bike racing. So
It's
that's
one funny thing too about these technologies is how powerful they are.
right.
So there's actually been some controversy related to Target, where Target was serving ads for maternity-related goods to teens, because their algorithm said that they should, and then it turned out the teens were pregnant.
Yeah.
Yeah. And it is just really amazing, because we are such social animals, so the connections that we have to our communities and our culture really kind of gives you a fingerprint of our cultural DNA, and you truly can extrapolate between people in a way that is almost magic.
Right.
Oh, Ed, go ahead, brother.
I'm sorry, just so I think what you're trying to say, and I think I understand this now, sliced subvectors might be the original vectors, some representation of a person on Facebook, their profile and all that. But you might slice it up for advertisers differently. Or
Exactly.
You might slice it up for maternity people.
Exactly. So these sliced vectors are like based on common feature, as you correctly pointed out.
Now, quick question, and again, we'll get on to the next slide, stat people, but is the motivation for the sliced subvectors completely that it provides like a kind of specialized perspective on classification, or is there computational motives as well?
There is a computation motive as well, because as you slice them, you have less number of mathematical representations to go through, less number of computations. So definitely it helps. And again, as you said, like the motivation was also coming from having like a certain feature, right? Because if you have a certain feature, it will help you in that particular business. And as you brought up like multimodal, similarly, it's like multi-feature at the same time. So yeah.
It's so cool. And then I always also think about this a little bit as like, because I think these things are a reflection of processes that happen in our mind.
Right.
Or at least I always like to look at them that way. And for some of these sliced subvectors, you could almost think of like anyone into sneakers? Any sneakerheads here? Big sneakerhead myself. There's a whole cultural classification layer where it's like, you see someone with panda dunks and you're like, and so it's just kind of interesting. It's like these, you might almost think of in the human context as little subcultures.
Right. So let's move to the next algorithm, which is like proximity-based graph index. And this one, as it says, HNSW, hierarchical navigable small world. This is just an acronym of like imagining each vector database as a world, and then you have subclusters as Stanley said, like subgroups or subcultures, right? So it's that. And if anyone is interested in knowing, but the data structure that this uses is called skip list. It's like just another list, but instead of storing the next pointer to the next list node, you store its like each node is basically a list. So you just store its head, and then you try to traverse through it to it. So skip list is a wonderful structure, and as you can see, like there are these layers, right? And you can imagine how each layer is a different list altogether, and this is like another optimization algorithm that researchers have come up with to do efficient searches on vector databases. Do you want to add?
Oh, I shouldn't, but it's just so beautiful. Because isn't there something kind of interesting happening in this picture where like each layer is a network?
Right.
But then
it's a graph.
A graph or a network. But then aren't the layers themselves a network?
Yep.
And there's actually some real depth that comes from that idea.
Right.
Anyway, this is so beautiful, man. What a good illustration.
Awesome.
A network of networks.
Yeah. And then same thing, again, like since most of these algorithms are computer science based, so people try to use the same tools that they are familiar with. So on one hand, we are looking at skip list, which is like a data structure of a list. Now, the next one is a tree. So we have seen so many applications of tree searches. So they said, okay, now let's try to do some tree-based indexing if it's possible, right? So ANOI is, again, as I said, these are all nearest neighbor algorithm. They are algorithms to find like who is the nearest to the centroid of that cluster. Where can I put this particular sample, like in which cluster? So this one is called ANOI, and it's kind of funny with the name. So it's approximate nearest neighbors. Oh yeah. So I don't know why they had to add oh yeah at the end of it, but it's so cool. And there are multiple well-known vector databases that use ANOI as their technique to do their queries. Do you want to add to that?
I do. I have always wondered about what was behind the naming of this. A lot of these techniques are actually used for a type of algorithm called an annoyance algorithm.
Right.
And so I wonder if that might have been the origin. So YouTube actually has a model built for each of you guys that tries to predict when you're reaching being too annoyed by ads. Like they try to predict when you're going to rage quit YouTube because there's too many ads, and then they'll show you 10 seconds less than that number. And so I've always wondered if it maybe annoy came out of annoyance algorithms. Kind of a silly thought,
but that's true. ANOI was done by Google, so it might be true.
It could be. I'm going to look into it, but this is so cool.
Yeah, awesome. Then this is the
LSH.
This is your favorite.
You guys.
I want you to get go for it.
No. Forgive me. I just actually past couple weeks have been working to use LSH in a non-linguistics situation, and so getting a lot of time to work with it. One thing that's kind of fun too is like there is this story in science and mathematics where we keep coming up with weirder and weirder geometric spaces, right? So we're like, oh, 3 dimensions. We live in 3 dimensions. We can think of that.
Right.
What about 100 dimensions?
Right.
What about 100 curved dimensions, right? And so it's kind of fun because it's almost like there's this story of trying to find more and more powerful ways to use nearest neighbor relationships. And sort of being like, oh, we have a phenomenon that's very complicated. Is there a way to imagine a space that's so complicated that all questions reduce to nearness in that crazy space? And then LSH is also just very beautiful. Maybe you should do the intro to LSH, and then I can share why it gets me sort of overexcited.
Sure. So as you can see on the slides, like each key is the mathematical representation, the embedding that we were talking about. Now we give it to this fuzzy hashing technique, which uses this function and tries to put them into hash buckets. So now when you're searching for your query, you don't have to go to the original embedding, but you can just look it in a specific hash bucket. Do you want to?
Yeah, absolutely. So
Yeah.
our k-nearest neighbor algorithm for this community here, that would be Jerry. And I'm kind of kidding, but I'm kind of not kidding, right? Because Jerry helps us get organized. He helps us figure out who to connect to. That's why we make y'all sign up on the hacksunday.com, invite your friends. Right? And it's so that Jerry can have the information of like, oh, this guy's interested in that. I'm going to connect him to this person. This person's interested in that. So I'm going to connect him to this person. But then you think about what happens as the community grows and there's more and more dimensions of variation and more people that our Jerry would have to keep in mind in order to make the right connections.
Right.
And this is a problem that Google has, right? Because you imagine the scale of their user base, and then maybe they have Ed, who's a new user, and they're going to try to search in their universe of billions of other users who is closest to Ed, who is most like Ed. And to actually go and compare Ed one-to-one with every one of the other billion users, and to do that for every single user,
It's computationally really expensive. Yeah,
extremely expensive, scales very poorly. This is the solution, which is they created a function that's kind of, well, the way that it's built is a little complex, but
right.
They've built a function so that you apply it to a single person, and it outputs almost what you want,
Right.
almost that classification, without needing to query the entire network. And
Right.
that's why it's locally sensitive.
Right. Awesome. And then as you explained with that, like for example, Jerry's taking Jerry as the centroid of it. Now he has created these buckets, which is like one is the science talk, another would be regarding Web3, another one you do is on artists, right? So now you have this hashing function in your mind, which puts us into separate cluster, right? And now when you want to search for like science, you will just go to your science bucket, right? And then you can pick those values. You can put, say, suppose some Mr. XYZ who is like into finance. So now you don't know where to put him. So you will try to like do some query with him. You'll try to ask, hey, you're in finance. Are you interested in blockchain? Then he goes to that crypto bucket, right? So that's the hashing function algorithm. Those questions that you will be asking this person are those hashing functions.
And yeah, just to mention one thing, LSH is seriously like maybe one of the core technologies behind Google.
Right.
They run LSH on just extremely large, unprecedentedly large data sets.
Right.
But anyway, here's just a fun and interesting thing. When LSH was developed to run on social data for Google, it was the only data sets in the world that were that big. And so in many ways, like the edge of data science in application to social media drives a bunch of the rest of the field.
Right.
But we're starting to have similarly large and complex data sets in other areas. So a project I've been working on for the past month actually is applying LSH to genomic data. And so actually mapping genomes to these kind of hashes and using them to understand what a genome does, like what kind of chemistry it performs. So it's just very interesting, and it's kind of, I think, part of the story of these technologies that they kind of start in big tech and then find other applications.
Yeah, that's really awesome. So next one here, it's like self-explanatory, and it does this sort of animation where you are putting all this training regarding regarding Shakespeare's literature into the database tower, and then you say, okay, I want to find a story which is done by Shakespeare and is related to tragedy. Now you haven't put any metadata saying like this is the story about tragedy, or this is the story about love and romance. But as you can see, when the query happens, it falls like closer to King Lear and Romeo and Juliet, which is a romance and a tragedy, whereas King Lear is also a tragedy-based novel. So this is the overall use that SCAN is doing. Basically, it is using CNN, convoluted neural networks, to find the nearest neighbor. As we are talking, like every time it is the nearest neighbor, right? And these are just the optimization algorithms for it. As you can see, it is doing some sort of compression based on neural network, so that you get like efficient and closest nearest neighbor for your query. Yeah, and do you want to add something to that?
Well, absolutely. I mean, it's just so cool that it's sort of like neural networks are how we create and interact with these spaces, because
Right.
it would be too hard for a human to kind of by hand put the words out in the high dimensional space.
Right.
And then convolutional neural networks are very interesting because it's actually like very explicitly their deficiencies that led to the invention of large language models.
Yeah.
The convolutional part of a convolutional neural network means it collapses a number of things down to one thing.
Yeah.
And then the idea would be that it's recognizing that a couple different things are really the same thing, and so it's okay to collapse them together and sort of compress the information that way.
Right.
But then it's also very possible to lose important information through
Right.
compression. And for that reason, convolutional neural networks sucked at producing language. Actually, if you remember the days of Google Translate where it was almost a comedy show, you know,
Right.
you put in something, you get out something so broken that you're like, whoa. That was all convolutional neural networks, and then it was all the desire to have a little bit of a better tool for interacting with these spaces that gave us LLMs.
Right. The GANs.
That's right.
Awesome. Again, someone wants to know this SCAN algorithm uses the Euclidean distance, as we had discussed earlier with that. So here's like the conclusion side from my end, and I did this sort of research to come up with the vector database comparison. So as you can see, I have listed down some of the technologies which are out there for vector databases. So Pinecone is one of the most used, and it's like free. So that uses the ANN, which is the approximate ANOI, as we all know, as the approximate nearest neighbor algorithm. The use case is real-time search and recommendations. Similarly, Waviate, and also one of them that I used was Single Store. They all use HNSW. So this was the layered-based approach. And again, as it uses graph, it is used for knowledge graphs, right? And then Elasticsearch is one which I used pretty much in my implementations. So it's like really good for text search and recommendation. So one of the applications that I did with Elasticsearch was I created this auxiliary database to our Postgres database where doctors could search for their appointments. And we had this, what do we call, like a call center where patients could call and change their appointments or change their doctors. And that's where it was taking like almost 3 minutes for our Postgres database, which had like millions of users, to search the appointment even we tried like different indexing mechanisms, but Elasticsearch was like a really good tool for us to find that, and it just reduced it to 300 milliseconds. I was very closely working with the managers of this call center, and they said like we really had to train our call center employees to talk to the patient about like weather and how their family is doing and stuff like that, and people were getting annoyed. So yeah, so this Elasticsearch really helped. It's a normal tool. It is based on Lucene. Lucene is Apache open source based sort of like precursor to vector databases. It's more of a document database, but people have found even using that document database could be a good use case for vector databases as well.
Myself, a big Elasticsearch fan, used on many key projects.
Right.
Do you have an opine on the Amazon hostile takeover of Elasticsearch?
Yeah. Of course, like when I used Elasticsearch back in 2017, it was open source, and we could recommend changes, and I was happy to take their source code and make certain subtle changes that were required specific for my use case. But now, since Amazon has taken them over, we do not have that liberty. And again, Amazon has taken this open source technology and made them commercial. So,
and it's kind of like, you know, I don't have too much of a leg to stand on to talk crap about Amazon. So grateful for the cheap servers, guys. Thank you. But at the same time, Amazon has this big vibe of like, hey, that's a nice open source project you got over there. It'd be a shame if anything happened to it.
Right.
So it's actually kind of one of the funny stories that actually, and push back on this if I'm not correct in terms of the kind of role in the space. But vector database has been along for a while. Elasticsearch was the leading database for most of the history in this area. And then right before this LLM stuff happened, Amazon did this like hostile takeover of the open source group. And the usage from my perspective really fractured. It's really kind of like a tragic story on some level.
Otherwise, if Elasticsearch was open source still, most famous vector database would be Elasticsearch. But
really
again,
created the space for Pinecone, and I have to say, love Pinecone.
Yeah, Pinecone is really cool. So yeah, this was my conclusion, and if anyone is interested, I think I have a small link up there. I'll share the slides once it's done. And here comes your part, Stanley. So this is the use case you wanted to share with everyone regarding graph databases and vector databases in general. So
absolutely, and it'll just be like a little addendum to the incredible presentation from Gaurav. Those slides were incredible. So much fun to talk about it. And forgive me, I meant to actually create a few more slides with this, but had some kind of help with slides lined up for yesterday, but family emergency happened. But anyway, this is like what a production data system looks like. It's kind of painful.
Blurry, actually.
And actually, let's see if we could zoom in maybe on the top left of it. Each of these nodes is a different type of data, and then we have a relationship. That's not the right part. Sorry.
Which one do you want?
Oh, bottom left part. The node that says sample. If we could zoom that in a little bit.
Oh,
Sorry, if you don't mind, if there's a cloud notebook for this, can Jerry please post it?
We do have a notebook that's kind of related to looking at embeddings that Gaurav had, and I think maybe we can get that shared, and then right after I'm done flapping my gums, we can jump into some collabing together if you guys want. But kind of just wanted to express sort of like one use case of this. So right here, we're actually looking at a marine science data system. So in the middle, you have a sample, and that just means someone went out in a boat, collected some water, sequenced the DNA in the water. And then the sample has a number of different connections. On the right, the sample's connected to a node that says MAG. And that is the actual genomic data that was found in the sample of water. And then over here on the left, you see it goes over to ecological event and then remote sensing. So remote sensing just means every time we sequence the DNA in the water, we also take a picture of it. So what we're attempting to do is understand what can we learn about the genomics of a system by looking at it visually and vice versa.
Right.
In order to understand those connections, though, we need to embed both pieces of data in the same vector database.
Right.
So on the left side, we have images. On the right side, we have sequences of ACTs and Gs, like we have genomes. And then we need to figure out how to put all of them in a space together with each other in the same way that Gaurav showed you. And again, it isn't always clear how to do that, but this is what comes out of these systems when we structure them properly with the help of large language models. We're actually quite confident that what we're going to be able to do is actually translate back and forth fluidly from a picture of a microbial ecosystem and the exact genomic data that it contains. And anyway, maybe even at a future talk, we could look at some embeddings together.
Sure.
With that data. And on that note, maybe let's get the Colab notebook back up and see if we want to mess around with it a little bit.
Sure.
You want to drop that in the Telegram?
Yep. Let me just this. Let's go to demo 1. Actually, it's here only. I can minimize this today. So here's the demo 1 as I was talking about. Let me post this in the Telegram channel, right?
Please.
Thank you. Right. Let's see if we have anything. Okay. So do you guys want me to go over this notebook again? We had gone through it last time. Okay.
Yeah, I mean, give people a second to open it up, but maybe while they're doing that, talking about it high level would be amazing.
Sure.
And so this is so like kind of like you were saying, this creates a specific set of embeddings that can let you compare two images well.
So this demo is basically, as you can see, you can give like any PDF URL. It uses Llama 2 because Llama 2 has like really good textual embedding already inbuilt in it. So I tried to use that, and then we just use those embedding and try to create our own vector data store on which we can do some semantic queries. So, and as shown over here, we are trying to use the cosine similarity. If we go back to our presentation over here, as you can see, it's using this particular formula, trying to find the closest distance between the 2 points using this cosine distance formula.
I love just distance metrics so much.
And then we create a vector data store, and over here I have said, can you tell me the concepts of safety fine-tuning. And as this document has some information about how to create vector databases and stuff like that, it was able to come up with certain answer for me. So it found out like these are some nodes which match with safety and fine tuning, and then based on that, it comes up with actual answer. So this has been generated by the Llama 2 LLM itself. So, and it's based on the vector data store that we have created out of that PDF. So this was the whole demo that this particular notebook does. Any questions? Yeah, so we did just to consume the PDF, the content in the PDF, we had to separate it out in different paragraphs. But then since Llama 2 has its own embedding and it knows how to cluster the text, it has done it. So I'm not creating my own embeddings, I'm just using, it chunks it itself, yeah.
The selection of an embedding to use in a system like this is kind of interesting, and OpenAI actually just released a new set of optimized embeddings.
Oh, awesome.
Question, how would something like this be used in like a RAG system?
Oh yeah, so based on that, we could create our own RAG system. For example, now I want to create like a store just for this particular PDF. So imagine like this is not a PDF, but it's like it's like cluster of PDF which are related to medical or related to law, immigration law, for example. So one could create a RAG system that will help you just get specific answers, not something related to whatever is there available on the internet or whatever a GAN could hallucinate about, right? It would be like specific to that particular domain. And that's where RAG systems or SLMs, as we were talking about it some time back, are really powerful.
And who knows what I mean when I say a RAG system? Does everyone know what RAG is?
You said it last week, but can you remind us again?
Absolutely, and it's an acronym, and so I should have said what it was. It's impolite to just use a naked acronym. But yeah, so RAG is Retrieval Augmented Generation. Mm-hmm. Oh, it's right there.
Yeah.
Oh my gosh, I should have pointed to that. And yeah, it's interesting. Like, has anyone had an LLM hallucinate on them?
Yeah.
So RAG is one of the main solutions to hallucination among other things, and it's basically, I like to describe it as a long-term memory for the model.
Right.
But essentially, just through these mechanisms that Gaurav has explained to us, a large language model that's asked a question can actually go find the bulk of the answer and then kind of inject that into the response.
Right.
It's very interesting. And, I actually we'll need to think a little bit about what a good next talk is. I think we should go a little bit more in the art direction for the next talk. But down the road, maybe we could present on fine-tuning together.
Yeah, sure.
And because that's actually one of the really interesting things is not just fine-tuning a model, but fine-tuning and ragging a model. Right. So sort of not just tuning a model so that it says things you like, but so that it takes things from rag and then rephrases them in a powerful way.
So just for audience, can you elaborate a little bit on fine tuning and like what is the difference between fine tuning and RAG, especially?
Oh, I would love to, but actually I would wonder maybe if you could go back to your slide and go back one or two slides to those beautiful animations you had of the actual networks rippling as the data passes through them. Because right there is what a neural network looks like. It's all these little dots that are connected by lines. And then I like to think of it as like the intelligence is stored in the dynamics of the rippling. like you see there's the bottom of the neural network, and it sort of shakes, and then the next layer shakes, and then the next layer shakes. And that's what a neural network is it's a data in, data out machine, and then as the data ripples through the network, it's changed.
Right.
So that's kind of what a neural network is, how it works, really obviously hand-wavy high level. And then how does it like get the intelligence though? It's this training process that we've talked about, right? And this, the training process for GPT-4, for example, it's estimated that it was 6 to 9 months of 25,000 large computers working together. Like we're talking the energy bill of a mid to large size city just to train one of these models. Crazy, right? And that is sort of like happening because there's so many of those little dots. For example, GPT-4 is estimated to have 1 trillion of those dots. They're all interconnected. So every time they feed new data through it, the data changes the values of every single one of those little dots. So it's sort of, you imagine 1 trillion different numbers that are constantly being updated and tested, and their interrelations are being messed with and understood.
So on the higher level, what you're trying to say, fine-tuning is basically changing those connections that are between those dots.
So fine-tuning, yes, is changing some of the dots, but not all the dots. So it might be something like we change just the last layer or the last 2 layers.
Right.
Or in the case of the most used technology, which is called LoRa, which stands for low rank adaptation, you actually add on a little extra layer of neurons at the end that are almost like the translator for the model. And then the translator learns to make the model sound a different way by taking its output and then restructuring the output.
Okay.
But overall, it's kind of like you're restarting the training, but you're only picking a certain part of the network, focusing your energy on getting that part of the network to sound like you want. And it turns out you can completely change the behavior of these models with just that little bit of tuning. Right. And then again, I like to call this giving your model a master's degree.
Nice.
It depends. There's a number of different approaches to fine-tuning and different ways to do it. It actually usually wouldn't be just a single layer. It could be. But yeah, as you add more neurons, the computational cost, it increases very quickly.
And you mentioned it was about 1 trillion nodes. Can you grab that mic? Thank you.
You can use it in the stand. That's better.
You mentioned, can you hear that?
Yes, yes.
You mentioned there's 1 trillion points in GPT-4. Any idea how many layers are in that?
Yeah, offhand, I'm not 100% sure. With some paper and a little time, I could work it out. So maybe after the talk, I'll do my best to give an estimate. The trillion parameters is somewhat misleading, though, because ChatGPT is an 8-way mixture model. So they actually trained about a 120 billion parameter model, and then there's 8 copies of it working together in GPT-4, although they do fine-tune those independently. So.
Nice. So that was demo 1. Let's move to demo 2. The demo 2 one, I hope it has those. Sorry about that. But what this this would do, it would take like almost 7,000 images that we have. That I found on the internet, and these are like 7,000 images of different celebrities. And what we did is, and this was also done by Single Store DB, which is just another database like Pinecone. So what Single Store DB people did, they basically came up with a mathematical function called dot product. If we go back to the slides, here is the mathematical function for dot product. So it's taking a dot product between two vector quantities, as known in physics. So this is the formula to do it, but doing this on data was something that that Single Store DB guys did, and they created like a traditional SQL sort of query that you can do on any sort of vector databases. And this is the same sort of technology that I used. And as you can see, let me go down.
The dot product is so beautiful.
Yep.
And one of the most important discoveries in human history.
True. It solves many physics equations, though.
It's maybe one of the most useful tools in all of physics. And then
Mm-hmm.
what the dot product does is you give two vectors, and the dot product answers the question, to what degree are these vectors going in the same direction?
Yeah.
Basically.
But we are using the same thing in vector databases. So as you can see I don't have the line numbers, but as you can see in the query, it's doing like a traditional SQL-like query. You can select a file name where dot product of vector is found out, and basically what this does, it tries to find out the images that are similar in features. I think last time we had whose picture did we have, Jerry? Yeah, some celebrity. So his picture was selected, and it could find like similar 5 pictures of them. Yeah, Alec Baldwin.
Yeah, that's what it was too. And it was very funny because it produced 2 that were wrong, but they were very Alec Baldwin looking dudes.
Right. I don't have that example today, but yeah, some people might take it and run it today and show us like different celebrities if they can come up with that.
And I would love someone to see if they could query William Rohan Hamilton. Any Hamilton fans here? The inventor of the dot product?
Oh, really? I don't know if he would be there in the celebrity database.
No, he might not be, but he's a big hero of mine. He was out for a walk with his wife, and they were just walking over a bridge, and he had a eureka moment, so he ran over and actually carved the equation for the dot product into the bridge. And it's still there. It's considered a pilgrimage site for mathematicians.
Wow.
And engineers.
Wow.
But then I always think about that anecdote and feel bad for his wife.
Yeah.
Any questions before we jump into the Colab notebooks? And then also maybe we should do another round of applause for...
Thank you.
I have to say, I do this stuff every day. It's been my career for 10 or 15 years, and I don't know if I've ever seen a crisper, sharper presentation of the good ideas. That was so beautiful, my friend.
Thank you. Thank you, Stanley.
I have a question. So all these vector databases.
Come on, Christina.
So I love that we've been studying a lot of different functionality today, or at least you've been introducing it to us in terms of similarities, in terms of vector databases and all the different ways that can be applied. But are they also working on models to study polarities? Because that could also be useful in many different contexts.
So could you elaborate on what sort of
polarities like dark, light, like some of them are a little more similar than they think, which is kind of funny,
Well, I mean, I would say sort of in the same way that these things learn to understand patterns of similarity, they necessarily also learn patterns of difference. So,
Right.
For example, when we were looking at examples last week, we looked at an example of gender as a dimension that is often part of these models. Because our language is so polarized by gender, it shows up very clearly in the embeddings what language is male and what language is female. And so I would actually say that's one of the very exciting things about these technologies is they allow us to quantitatively see these kind of polarizations or biases that exist in our language day to day. So we can actually see that there is this big difference in language related to gender, which I think most of us are very familiar with as a core injustice of our society.
Yeah, and just like these are two different school of thoughts, right? One scientist might say, okay, we are finding similarity, so we don't have to find dissimilarities. Another scientist would say, oh, we need to find the similarities so that we can cluster the similarities together. So like doing one will automatically find the other. So you don't have to do it explicitly as such.
Thank you.
Oh, such a good question too.
Yeah,
And
that shows everyone was listening to us.
no, I have to say, I thought it was so good, and thanks everyone for being here. And if there's no more questions, we can wrap it up. And I'm here if anyone wants to goof around with the collab or get some help with it. And then we can also talk more in some little breakout groups for at least a moment or two, I'm sure.
Sure. Thank you.
Woo!
Awesome. Trick, are we out?